Hey everyone, it's Clayton from Design Build Make. So the other day, I came across this video of a really cool clock made by German artist Felix Vorreiter. The whole thing looks straightforward at first glance. It's just a simple box with a piece of string winding through it, and the string has some black paint marks on it. But when the string is pulled at just the right position, it actually forms numbers and it shows the current time. And so every minute the string moves forward a little bit and it displays a new time there. I personally found this clock incredibly mesmerizing. When you start looking at it more, there's actually a lot of complexity here. All of the markings have to line up just perfectly to show the current time, and there's a lot of string for each minute displayed. In fact, the original artist only ever painted enough string to run the clock for 2 hours at a time. If he wanted to make the entire 12-hour clock, he said it would have actually been 0.7 miles worth of string. With 0.7 miles of string, this build is completely impractical, and it really prevents this art piece from becoming a truly functional clock. To help us visualize the problem a little bit more, I've made a replica of the clock here, and everything is measured out to be roughly the same size as the original clock. The only difference is, instead of painting marks on string, I've actually put beads on this string because I found it a bit easier to get exact measurements that way. So as you can see, I currently have my replica set up so that it shows the time as 1 o'clock. Now let me just say, even from building this single minute display, it became very clear how you could add up to 7/10 of a mile for the entire clock. I mean, this 1 minute already has to loop back and forth 5 times. In the end, it took 235 beads, and it's almost 5 feet long. But building this replica also made me realize how much redundancy there is in each string. First off, look at the margins here. There is so much white space on either side that's not really being used for anything. But I also realized how much symmetry there is. For instance, the first row here is exactly identical to the 5th row. And the same holds true for the 2nd and the 4th row. In fact, only the 5th row is unique on this particular minute. And now that's not true for every single minute, but it's pretty easy to see that there's going to be a lot of repetition across 720 minutes. And so that's when I got to thinking, I wonder if there's a way where we can take advantage of all this repetition and all this wasted space in order to represent all of these times in a much shorter overall string. In particular, is there a way where we can overlap the individual strings for each minute so that they make use of each other's margins, or so that they reuse pieces of each other's display? So I want to figure out a way to take each of these strings that represent a minute and overlap them as much as possible. In other words, I want to figure out the shortest final string of beads that contains every other string of beads within it. The good news is this is actually a well-known problem in computer science. In fact, it's used for things like genetics research and even early antivirus programs. Let's look at a little toy example so we can see how this works. Let's take this very simple example where we just have 2 input strings. Now in reality, we will have 720 of these, 1 for each minute, and they'll be much, much longer. But for this example, we just have 2. And so if our goal is to find out the shortest string that contains both of these, it's actually pretty straightforward. All we have to do is align them so we have the most overlap possible, and create a string that's the merge of those 2. Now as you can see, this string only has 4 beads instead of the total 6 from our input, and yet it contains a blue, white, white, and also a white, white, blue sequence. And so we could get rid of these 2 and just use this to represent both of them. So you might say, okay, that's pretty straightforward, but there were only 2 strings. What do we do if we have more than 2? Well, let's take another example. So let's say we have our 2 strings from before, but we also add a 3rd one, which is all whites. Well, we can follow a similar pattern to before. We just look for the greatest overlap between each pair and choose the pair that has the most overlap. So these 2 overlap by 2, these 2 overlap by 2, and finally these also overlap by 2. So really any pair is all right, they all have the same overlap. So let's take these 2. As before, we line them up and we combine them into a single string that contains both of them. And now we can get rid of these two, just like we did before. And this brings us to a similar case as before, where we just have two strings. So again, we compute their overlap, and we see that they can overlap by 2. And we create the merged version of them, which looks like this. And so now we can see that this final one only has 5 beads, even though the sum of our inputs was 9 beads long. And so we've actually saved quite a bit here. But it's not always that simple. Let me go back to the 3-string example from before. So here again, we have 3 strings. And as I said, they all have equal overlap. So what if we chose a different pair than before? What if this time we chose to combine these two? If we did that, we would get a string that looks like this, just like our 2-string example at the start. And so we'd throw these 2 away, and then we would continue our algorithm with these 2 strings as our inputs. And you might see the problem. By choosing that other pair to start with, we've actually created blue bookends on the new merged string. And so there's nowhere for this all-white one to go except on the very end. And so that gives us something that looks like this. And this is 7 beads long, which is still shorter than the sum of our inputs, which was 9 beads long. But it's much, much longer than the one we got earlier, which was only 5 beads long. And this is an unfortunate consequence of the algorithm that I've just outlined. When there are multiple paths that we could go down, we'll never know which one is the best unless we actually try all of them. And so you might be thinking, Clayton, why don't you just try every possible combination, right? I mean, if there are some that will give us much better answers, we shouldn't just try one and hope that it'll work. The problem is, for something as big as our clock, with 720 minutes, and each one with more than 200 beads, if we wanted to actually try every combination, we would never finish. There are actually many, many, many orders of magnitude more combinations that we could try for this problem than there are atoms in the observable universe. So we have to do something approximate and just hope that it works. We can actually do slightly better than just hoping. I'll run it a few times with some randomness in there, and we'll see how much variance there is between each run. If we see that the answers are mostly pretty close in length, then probably we're not missing out on anything. But if they vary a lot, that's a signal that I probably need to run this a lot more and see if we can get a lucky one. Our version of this problem does have one more wrinkle in it compared to the standard version that computer scientists have been studying for some time now. And that's that we don't really care what color the margins are, right? They could be white, they can be blue, they can be speckled, they can be whatever. We really just want them to be whatever gives us the most compact representation in the end. And so the normal problem assumes that all of the input strings of beads are known at the start. But for us, we know pieces of them, and then other pieces are kind of wildcards. They can be whatever they need to be in the end to give us the best final answer. This likely means that there's room for more research and optimization to make our algorithm work even better for this special case. But for now, I'm going to follow the same methodology and see what happens. Now, as a reminder, the original clock just put each string of beads, one for each minute, end to end. And this came out to a final string length of about 0.7 miles. And so I ran the algorithm several times because, again, it varies from run to run. And at best, we can reduce that by about 60%. And that's pretty good, but it still leaves us with a quarter of a mile to maybe even 3/10 of a mile as our final answer. And that's not something I'm looking to build. But I did output each version, the original and my best one, as an image where blue pixels represent blue beads and white pixels represent white beads. As you can see, the original one has these really clear white gaps in between each minute. And that's the unused white space that I first noticed. And you can see that these gaps also get smaller near the bottom because that represents 10, 11, and 12 o'clock, the hours where we actually have 4 digits per minute instead of just 3. So those gaps get a bit smaller. But really the takeaway is there is just so much white space here. When you look at the new one, not only is it more dense with more blue beads, is just much smaller, right? I mean, this is the 60% reduction that we talked about. It's really hard to see any patterns on the new image because we've kind of done away with all of the natural patterns that might happen from putting each minute sequentially one after another, and we've just figured out how to fit them in as best as we can. Now, I didn't build the entire quarter-mile long string of beads, but I did look for the densest part of our solution, the part where the most individual minutes overlapped each other in one place, and I built a string that shows how that works. So let's take a look at that. Okay, let's see what this looks like. So we start off with 204, and the green bead is in the bottom of the 2, right here. Next up is 616, and the green bead is just on the bottom left bearing down here. So it's not actually being used in the clock, but it hasn't traveled very far yet. Okay, next up we have 919, and the green bead has made it all the way up to the top left bearing. Again, it's not actually being used for this current time, but it hasn't traveled more than a couple rows. Here's the 4th time, which is 551. You see the green bead made another appearance inside of the actual time. And this actually makes sense, right? Before, the green bead was the bottom middle of a 2 in 204, and now it's the top middle of a 5, which you can see the top of the 5 looks like the bottom of the 2, the top of this 5 looks like the bottom of the 0, and the top of this 1 looks like the bottom of the 4. So it's really just reflected from the bottom row to the top row. And finally, we have 313. This is the final time, and you can see that the green bead is just right at the beginning of the string for this time. So now we've made it through 5 unique times, and the green bead has only traveled about the length of 1 of our original strings. For this project, I set out to take this awesome piece of art and see if I could actually make it a functional clock. And in the end, my efforts weren't quite enough. We did get a 60% reduction in the length of string needed, but it still came out to just a very, very long and impractical string. However, I think there are a few things in the future that we could try. For instance, you could use more strings for smaller pieces of the clock. Maybe 1 string for the hours and 1 string for the minutes, or 1 string for each digit. This kind of reduces the space that we have to solve and would make the problem much simpler. Also, each number is currently composed of 5 rows of strings. We could probably cut that down to just 3 or 4, just to make the final solution a bit shorter. But there is one major problem that I haven't really talked about yet. So with the original clock, if the time was, let's say, 3:05 and you wanted to get to 3:06, you just needed to move the string a few feet to get to the next time. But with my version, we have kind of jumbled up all the times, so they're not next to each other anymore. So 3:05 may be dozens of feet away from 3:06. And this can be a real problem, because you really want your clock to show the current time as much as possible, which means you want to spend as little time as possible switching between 1 minute and the next. And so that means that if you only want to give a few seconds to switch from one time to the next, you need to get there really quickly. And if it's dozens and dozens of feet of string away, your motors need to spin really fast to get you there. Now, there are probably some things that we could do in the algorithm to help fix this. For instance, we could penalize any solutions that put sequential numbers far away from each other. But still, that could harm how much reduction in size we get. In the end, this clock is awesome. The computer science is really, really interesting, and I had a lot of fun building the prototypes. So I'm not that upset that I wasn't able to get a fully functional 12-hour clock out of this. But if you have any ideas on how to make this even more efficient, leave your idea down in the comment, and maybe I'll come back to it in a part 2. As always, if you enjoyed this video and you want to see more like it, please give it a like and subscribe to my channel so that you know when the next one comes out.